Now today I will tell you about the experimental proof of uncertainty principle. This is done by the diffraction of the electron beam by a narrow slit. This topic was also included in the syllabus of RVSE, CVSE and that ICSE, but nowadays it has been deleted from the source, from the book, because some of them understand that this is not of use. In Corona, this was deleted. But this is very important experiment, and this is tells you that how this uncertainty principle can be proved experimentally. As I have told you that the uncertainty principle was given by Heisenberg in 1927, and for this he was awarded the Nobel Prize for Physics. The proof of this one that the experiment goes that I will illustrate today. So now let this is a narrow slit. This is narrow slit. This is the electron beam. And here we have the diffraction pattern on this screen. This is now slit A, B. Now the width of the slit is delta Y. Now this is being diffracted. Let here this is being diffracted at this angle. So here we have a diffraction pattern. This is the diffraction pattern. This is the angle theta, and this is also the angle theta. So now I have shown you this electron beam. This is the slit of thickness delta y. Delta y equal to thickness of slit AB, and this is an electron beam. This we say better to electron beam. Electron beam. The electron beam is diffracted by slit AB, and its diffraction pattern pattern as central maximum and other minima. So this is now first minima, second minima, third minima. This is now first minima, second minima, third minima. So this is now your central fringe of large thickness. So now this thickness may be equal to this the thickness of this slit AB. So uncertainty in the, so now we can have, let theta equal to diffraction angle. The uncertainty in position of electron beam is equal to delta y. So now for minima, path difference delta is equal to delta y into sin theta. So for minima that we have this delta y sin theta is equal to n lambda. So for first minima, n equal to 1, so this delta y sin theta is equal to lambda. So this delta y will be equal to how much? Delta y equal to, now this lambda equal to h upon p, p the momentum. So now electron is moving in this direction, so this is now x direction, and the momentum can be resolved into two components, so one along this x axis, second this y axis. So now we are having this in this way, this is x axis and this is y axis, this is now electron beam. So this is equal to lambda upon sin theta. This is number 1. Let momentum of electron is equal to P. So now we have this beam in this way, so we can resolve it into the two components. This is the momentum P in this direction, this is now angle theta, and this angle is also theta. So now we can have two components, one is along this P cos theta, and this is now P sin theta. P sin theta. Similarly, on this side we have this momentum P, and we can have this P cos theta, and this is now your P sin theta. So this is along x-axis and this is along y-axis. So now uncertainty in principle, uncertainty in the momentum along x-axis. Change in momentum along x-axis. So this px equal to p cos theta minus p cos theta, so this is equal to 0. So this is now your delta px. We can have better delta px. So this delta px is equal to 0. Now along this y-axis, change in momentum along y-axis, this delta py, this is equal to, now this we take to be now p sin theta minus p sin theta, because this component is in the opposite direction of this one. So this is now equal to 2p sin theta. So this is now uncertainty in momentum along y-axis. It is uncertainty in momentum. So now this we have equation number 2. Now then we multiply this number 1 and number 2. So multiplying equation 1 and 2. So what we have, this delta y into delta py, this is equal to lambda upon sin theta into 2p sin theta. So now this sin theta and sin theta will cancel. So this is now your 2p lambda, and this is not 2p lambda. 2p lambda equal to h upon p, as I have told here. This is now de Broglie wavelength. De Broglie wavelength. De Broglie wavelength. So now this p and p will cancel. So we will have this delta y into delta py is equal to 2h. This is now equation 3. But according to principle of uncertainty, according to principle uncertainty principle, delta y into delta py is greater than h cross upon 2, where this h cross equal to h upon 2 pi. Here h is Planck's constant. Where h equal to Planck's constant. So it can be seen that this product in equation 3 is equal to 2h, and this 2h is greater than h cross upon 2. from equation 3, it follows that delta y into delta py is greater than equal to h cross upon 2, which is the uncertainty principle. So this is the proof. It is experimental proof. Proof of uncertainty principle. So what the product of the uncertainty in position and momentum must be greater than equal to h cross upon 2. So here we are getting this 2h, and 2h is more than h cross upon 2. So definitely we can say that this experiment have a sound proof of the uncertainty principle that was given by Heisenberg. So this is the experimental proof. So thank you very much.